Hi everyone, welcome again. In this video, we will look on how to solve the other case of the heat equation, which is that partial differential equation. So in this case, we will consider the heat transfer along the rod as previously, but in this case, it is insulated end, which is that at the end of both rod is insulated. So we have the boundary condition, which is that at derivative of temperature at x equal to 0 and x equal to L equal to 0. Then we have the boundary condition of du dt or dt dx. dt over dx is equal to 0 at x equal to 0 and at x equal to L. So that is the difference between the first case that we looked at previously. So the difference only for the boundary condition, which is that insulated end, and it also have the initial condition for the cases. And again, we have the PDE, which is that heat transfer coefficient, similar as previously, and we have the thermal distributivity alpha, which is the content of thermal conductivity, specific heat, and the density of material. So how to solve this one? Similar as previous we looked before this, but in these cases, basically the solution is u is xt is equal to fx gt. Then we have the boundary condition, which is that ux or dx dt, we write down as ux at s equal to 0 is equal to the function of derivative of f at 0 and gt. And similar for the other boundary condition, which is that ux at x equal to L, t is equal to f at L and gt. So we use the separable operation as previously, which is that we have du over dt is equal to alpha squared du t squared u over dx squared, and then we differentiate the u here in the form of dfx gt over dt is equal to alpha squared dfx gt over dx squared. So from here we will have f g dot is equal to alpha squared f double prime g, and then from here we can split into two equation since this is the constant. So we will have we use g dot over alpha squared g is equal to f double prime over f, and then this one basically is equal to lambda, and we can arrange the equation become two differential equation, which is that this one is second order and this one is the first order PDE. So from here we will solve one by one for the each equation, depend on the boundary condition given, which is that we need to make sure the boundary condition is satisfied with the equation. So similar, we have the boundary condition is depend on the lambda, which is that lambda equal to 0 or lambda bigger than 0 or less than 0, and we check first with the lambda equal to 0 one by one, and when we check the boundary condition is satisfied for all the condition from here, and then one of the solution is fx is equal to ax plus b. So this one is satisfied the boundary condition given. And then we move to another condition of lambda, which is that lambda is bigger than 0. So again, from here we have the two real root when we solve the second order differential equation, and when we apply the boundary condition, there is one condition that not satisfied, which is that at x equal to L, so this one is not satisfied the boundary condition, so we cannot use this one as a solution. And then we try to look at the other condition, which is that alpha or lambda is less than 0. So this one is complete root, and we have this kind of solution. So this one is solution. So we need to differentiate to apply the boundary condition, and then this boundary condition also satisfied with both condition, which is that x equal to 0 and x equal to L. So for this one, we have two condition or two solution of fx, which is that fx equal to the first one, which is that this one, ax plus b, and another condition, which is that a fx equal to a cos n pi x over L. So we have the two condition or two solution for the fx. The next we move to the g, which is the second or the first order differential equation. Similar, we doing the same one as previously, which is that we apply the boundary condition. We solve the first order differential equation first, which is that we have the solution, and then we apply the boundary condition. We know that the boundary condition satisfy with the equation, or with this case, the case is lambda equal to 0 and lambda is less than 0, that we already found in the second order differential equation. So we apply for both condition of this one into the equation, and at the end we got the solution of the case for this case is ux is equal to this one, or we can use the superposition to simplify the equation. So we have this solution of the second case. Again, this one is the solution for insulated end of a rod, and then we again for the third step we apply the initial condition, which is that the initial condition given is fx. So we need to determine what is the value of a0 and an by using the Fourier series, and then from here we can solve the solution, or we got the real solution of case 2 of heat transfer coefficient, heat transfer for PDE. So that's all for the case 2 of heat transfer problem by using the partial differential equation. So again, we meet again in that next video. Thank you very much.